Something unusual appears to be unfolding, not as a single dramatic event, not as one unmistakable signal screaming for attention, but as a convergence, quiet, distributed, and easy to dismiss if viewed in isolation. Individually, each event fits within established scientific frameworks. Earthquakes happen, the sun flares, planets move in predictable paths. Interstellar objects pass through from time to time. None of this is extraordinary on its own. And yet, when these signals are placed side by side, when their timing overlaps, the pattern becomes harder to ignore. By late 2025, researchers in different fields began noting stress indicators in systems that rarely attract attention at the same time. Deep beneath Taiwan, a magnitude 6.6 earthquake ruptured nearly 150 kilometers below the surface. This depth alone places the event outside the category of typical destructive quakes. Most earthquakes occur in Earth's brittle upper crust, where rock fractures under pressure. At depths beyond 100 kilometers, temperatures and pressures are so extreme that rock is expected to deform plastically, to flow rather than snap. When rupture occurs there, it suggests that stress is behaving differently than standard models predict. Taiwan sits atop one of the most compressed tectonic environments on the planet. The Philippine Sea Plate continues to subduct beneath the Eurasian Plate, loading stress into the mantle year after year. A deep focus earthquake does not signal imminent catastrophe, but it does act as a pressure gauge, revealing forces accumulating far below where humans normally observe them. At nearly the same time, attention turned upward. The Sun entered an unusually active phase. Multiple M-class solar flares were followed by several X-class eruptions, the most powerful category known. These events release enormous amounts of energy, flooding space with radiation and charged particles. When they reach Earth, they compress the magnetosphere, disturb satellite operations, and increase radiation exposure in near-Earth space. Solar physicists note that this behavior is consistent with solar cycle 25 approaching its maximum, a period when the Sun's magnetic field becomes unstable and prone to violent reconfiguration. This activity is not unexpected, but the frequency and clustering observed in late 2025 quietly raised eyebrows within the space weather community. Then, there is the geometry. In January 2026, 7 major bodies, the Sun, Mercury, Venus, Earth, Mars, Jupiter, and Saturn, will occupy a relatively narrow span of heliocentric longitude. This is not a perfect alignment. Astronomers are careful to emphasize that planetary alignments do not cause disasters. But this configuration represents one of the most compressed planetary geometries seen since 1936. Publicly, scientists dismiss dramatic interpretations. Privately, some researchers explore whether such configurations might slightly alter gravitational and electromagnetic stress distributions within systems already operating near critical thresholds. Not enough to cause events, but potentially enough to modulate timing. None of this proves anything extraordinary, but science has never advanced on certainty alone. It advances when independent systems begin to show unexpected synchronization. And into this convergence entered something entirely uninvited. An interstellar object designated 3I Atlas passed through the inner solar system, material formed around another star, arriving without warning and leaving little time for study. Interstellar visitors are among the rarest objects we can observe directly. With only 3 confirmed detections, scientists lack the statistical foundation to define what normal even means. Yet even within this limited sample, 3I Atlas stands apart. After reaching perihelion in late October 2025, standard comet models predicted rapid degradation. The object had likely spent millions of years in near absolute zero before encountering intense solar radiation. Fragmentation would have been expected. Instead, activity intensified. Observations revealed sustained outgassing, a rapidly expanding coma, and structural coherence that persisted longer than predicted. By mid-December, astronomers measured a coma approximately 185,000 kilometers across, larger than Jupiter itself. The tail extended hundreds of thousands of kilometers, while an apparent anti-tail suggested complex dust geometry and non-uniform material release. None of these features are unprecedented in isolation, but together they form a statistically uncommon profile. Spectroscopic data added further tension. Carbon dioxide emissions remained prominent at distances where water ice sublimation should dominate. This inversion hints at either an unusual internal structure or subsurface reservoirs exposed only after thermal cracking near perihelion. Some researchers suggest that prolonged exposure to interstellar radiation could alter volatile distribution in ways rarely observed among solar system comets. Polarimetric measurements deepened the mystery. Certain wavelengths exhibited negative polarization, a rare signature indicating dust grains with unfamiliar optical properties. One hypothesis proposes that cosmic ray bombardment over interstellar timescales may modify surface chemistry beyond what we typically observe closer to the Sun. Jets emerging from the nucleus appeared irregular and time-variable, implying rotation and internal asymmetry. These jets can generate small but measurable thrusts, subtly influencing spin rates and stability. While all of this remains within natural explanations, the clustering of anomalies is difficult to dismiss. And once again, timing intrudes. As Earth experiences heightened solar activity, tectonic stress indicators, and an upcoming planetary compression, 3I Atlas is passing through the gravitational center of this configuration. Classical physics suggests planetary gravity is too weak to matter. But stress is not the same as force. In nonlinear systems, small influences applied at the right moment can shift outcomes already near critical thresholds. This does not imply causation. It implies modulation. For now, no one is claiming intent. No one is claiming design. No one is claiming threat. But the pattern is forming. And science has learned, repeatedly, that when independent systems begin whispering at the same time, it is worth listening. As the calendar moves closer to January 2026, researchers are becoming less comfortable treating recent events as isolated curiosities. Not because any single measurement breaks the laws of physics, but because too many systems appear to be under stress at the same time. In complex environments, coincidence is common. Convergence is not. One of the least visible but most influential developments in this story has come not from telescopes or satellites, but from algorithms. Artificial intelligence systems are now deeply embedded in astronomical monitoring. They do not search for meaning. They do not speculate. They simply compare incoming data against historical patterns and flag deviations. When something behaves outside expected statistical envelopes, the system raises a marker. Months before public discussion intensified, several machine learning pipelines quietly flagged 3I Atlas. Not because it exhibited one dramatic anomaly, but because many moderate anomalies clustered together. Brightness fluctuations that refused to settle. Outgassing rates that did not decay on schedule. Jet activity that suggested internal asymmetry rather than surface-driven sublimation. Polarimetric values that sat just far enough outside the norm to be uncomfortable. Individually, none of these trigger alarms. Together, they form a profile that algorithms label as low-frequency behavior, patterns rarely observed because the sample size itself is so small. This is where discomfort begins. Interstellar objects are statistical outsiders. With only 3 confirmed detections, scientists cannot rely on averages or trends. Every new visitor forces a recalibration of what models assume. In this context, 3I Atlas is not just another comet, it is a stress test for our understanding of matter shaped beyond the Sun's influence. As the object moves outward, most models predicted stabilization, cooling, decline. Instead, its behavior remains dynamic. That persistence matters. Long-lived activity suggests that energy release is not confined to a thin surface layer. Something deeper may be involved, whether structural fractures, volatile pockets, or compositional layering shaped by millions of years in interstellar space. None of these explanations are exotic, but they are rarely observed in combination. And once again, timing refuses to stay out of the conversation. As 3I Atlas traverses the inner solar system, Earth is entering the most active phase of solar cycle 25. During solar maximum, the Sun's magnetic field becomes increasingly chaotic. Coronal holes expand. Solar wind density fluctuates. Magnetic reconnection events accelerate charged particles toward the inner planets. Earth's magnetosphere is designed to absorb this punishment, but it does so dynamically, stretching, compressing, and reconfiguring in response to solar input. During periods of sustained activity, the system becomes more sensitive to variation. This is where planetary geometry quietly re-enters the frame. In January 2026, the compressed configuration of major planetary bodies does not exert catastrophic force. But force is not the only variable that matters. In magnetohydrodynamic systems, boundary conditions matter. Orientation matters. Timing matters. Some physicists explore whether compressed planetary geometries can subtly alter heliospheric structure, slightly reshaping solar wind flow lines or magnetic field topology. If so, Earth's magnetosphere could respond differently during peak solar activity than it would under identical conditions spread across time. These ideas remain speculative, but they are no longer ignored. Meanwhile, Earth itself continues to signal stress. Deep-focus earthquakes are rare indicators. They do not break cities, they do not generate headlines, but they reveal pressure behavior far below the crust, where energy accumulates silently. When such events coincide with increased solar input and magnetospheric compression, researchers pay attention not because they expect disaster, but because systems rarely peak simultaneously without interaction. This does not mean one causes the other. It means they may be coupled through timing. Coupled systems do not require strong forces to influence outcomes. They require synchronization. And synchronization is exactly what unsettles researchers now. Astronomy, geophysics, space weather, machine learning. Each field, working independently, is flagging irregularities. Not extreme ones, but persistent deviations from expectation. History offers perspective here. Major shifts in scientific understanding rarely announce themselves clearly. They emerge during periods when existing models still work, but no longer work comfortably. When exceptions multiply. When disclaimers grow longer. When phrases like "within natural explanations" begin appearing more frequently than explanations themselves. This does not signal danger. It signals incompleteness. 3. Atlas may ultimately settle into a perfectly ordinary category once enough data is collected. Solar activity may decline without consequence. Earth's deep mantle may release stress gradually, as it often does. January 2026 may pass unnoticed by anyone outside scientific circles. That outcome remains entirely plausible. But so does another, one where this convergence forces refinement, where models are adjusted, assumptions rewritten, and boundaries expanded, where interstellar objects are no longer treated as scaled-up comets, but as fundamentally different archives of cosmic history, where planetary geometry is re-examined not as myth, but as a subtle modulator of already strained systems. Science does not move forward by declaring certainty. It moves forward when patterns refuse to disappear. This is not a prediction. It is not a warning. It is not a claim of intent, design, or threat. It is an observation. Multiple independent systems are speaking at once, quietly, cautiously, and just loudly enough to be heard by those who know how to listen. And when that happens, history suggests only one responsible response: Pay attention.